Your head explodes with dark forebodings too. I'll see you on the dark side of the moon. I'll see you on the dark side of the moon. And if the damn explodes in your ear, you shout, but no one wants to hear all that you taste and all that you love. All you create and all you destroy. Oh, yeah. All right, I see 3 people. We'll wait another minute or two. Okay, I'll get started now. First, I'm going to talk about a little bit of a different book situation. I just checked the bookstore website, and for some reason, they aren't yet showing the textbook for my math methods class in fall. Most or all of you will be taking that class, but this is the book, Mathematical Methods for Physics and Engineering by Riley, Hobson, and Bentz. I want to say 2 things about this. First of all, I chose this book even though it is not the book that the last instructor used, not because there was anything terribly wrong with the last book, but because this book I think has a little bit of a better introductory survey of things that hopefully you saw before, and I think that's important. Also, it's got a little more exhaustive catalog of topics, so it's good to keep as a reference book. So that's the book that we will be using in fall in math methods. I don't know when the bookstore website will list it, but I'm giving you plenty of advance notice to look for it. If you want to try to get it cheap, it doesn't look like there are too many cheaper paperbacks on Amazon, but you have all summer to hunt the internet for cheap editions. There's probably somebody who will save you $3 by shipping it from Australia via kayak. Feel free to order that. Just make sure the kayak arrives by late August. The other book we'll be using is A Student's Guide to Fourier Transforms, which is much cheaper. The paperback new goes for $28 on Amazon. There are cheaper paperbacks. Well, actually not that much cheaper. You could get an old edition if you want to. There are old editions. I won't fault anyone for getting the 2nd edition, which is actually what I still have. Although strangely enough, Amazon is showing, that used versions of the 2nd edition go for $6 or $7. So go ahead and get that. Again, you have all summer to find a cheap seller if you want. And finally, although not required, it is recommended, Mathematica Demystified. There's a ton of these books out there on how to use Mathematica. I just happen to like this one, but you can get, it's not required, it's only recommended. You can get any Mathematica book you want. If you do nothing else with your summer, spend some time learning Mathematica. For just about every homework assignment in this class, at least every big problem set, I've posted at least a few of the solutions in a Mathematica file for those who want to practice with Mathematica. So if you do nothing else, before the end of the semester, download all the Mathematica files that I've posted on Blackboard. Get a free Mathematica license. The university has a subscription, and I've posted instructions for that on Blackboard, and practice with that. It's not going to be an absolute requirement in fall, but it is very strongly recommended because Mathematica is better than a graphing calculator for a lot of the functions that we'll have to work with. Any questions? Okay, then let's start with relativity. Now, last time we talked about how velocities change when you go from one reference frame to another. Now we're going to see what the implications of that are for momentum conservation and energy conservation. And we're going to start with a simple collision, and this is all in the textbook in section 8.2. And we've just got a particle of mass m hitting a particle of mass 2m. The particle of mass m has a velocity of 3/5, and the particle of mass 2m is initially not moving. Now, if Newtonian mechanics is valid, then we can solve for the velocities. We have two unknowns. We'd have two equations to solve: momentum conservation and kinetic energy conservation. And if we did that, these would be the velocities after collision. And you can verify that before the collision, the x component of momentum was 3/5 m plus 0 times 2m, or just 3/5 m. And after, it's still 3/5 m. This is if Newtonian mechanics is valid. You know, we plugged in a big number, but so what? Now here's the thing. We know, at least in Newtonian mechanics, that momentum conservation is valid in all reference frames. And in relativity, we operate on the assumption that whatever the laws of physics might be, they must hold in all reference frames. So if there is a quantity that's conserved in one reference frame, and that conservation is not just some fluke of some little trick of how the numbers happen to work out in that case, but a general fact of the universe, then it better be conserved in all reference frames. So let's jump to the reference frame of this particle with mass m, all right? So we're jumping to a frame moving with a velocity beta equals 3/5. Well, now the velocity of this particle before collision is minus 3/5. So our momentum before collision is minus 6/5 m. Now that in and of itself is not a problem. It's not a problem that the momentum before collision is different in different reference frames. As long as whatever the momentum before collision might be in this reference frame is equal to the momentum after collision in this reference frame. Because a conservation law is not a statement about the value of a quantity. The law of conservation of momentum doesn't say all momenta are 3/5 m. It says that the change in momentum is 0. Well, then fine, we take these velocities and we do the velocity transformations on them to say, all right, if somebody in this reference frame measured these values for velocities of objects 1 and 2, after the collision, they should measure these velocities, minus 5/7 and minus 5/19. And then we plug those in and calculate momentum. We take minus 5/7 and multiply by m. We take minus 5/19 and multiply by 2m. We add them and we get something other than 6/5. And so we conclude that momentum conservation, if we use the Newtonian definition of momentum, does not work in relativity. And furthermore, I'm going to have you on Friday's homework assignment take all these numbers and calculate kinetic energies before and after in one reference frame, and see that in the reference frame where we initially did the calculations, energy conservation worked. But then in a different reference frame, energy conservation does not work if we calculate with Newtonian kinetic energy formulas. Any questions so far? Anyone? Anyone? Bueller? Bueller? All right, this example is in the textbook for you to refer back to. So there's two possible ways we could approach this. One is we could say maybe conservation laws don't work at all. This should be a last resort. It is worth noting that there were a few times in the early 20th century where people nearly gave up on conservation laws for microscopic processes, but in each case, they found a way to make it work. They found that actually the energy, momentum, and angular momentum are conserved. We just have to be very careful about how we define them, and we have to be very careful about accounting for all the particles. So the next possibility is that maybe momentum and energy are conserved. It's just that the quantities we defined are only valid at very low velocities. So what we're about to do is a guess, and the only justification for this guess is not logic, it's not some strong theoretical principle, it's the fact that in countless experiments every day it works, including experiments that are done, frankly, in hospitals every day with the positron emission tomography. So Newton defined momentum as m dx over dt. And this is the ratio of two things that are measured in specific reference frames. Two things that we don't necessarily agree on. Let's try replacing one of those quantities with something that we do all agree on. And one thing that we do all agree on is d tau. Now I have to be careful there. Obviously not every observer measures d tau on their own clock, but every inertial observer could use their measurement of dt and their measurement of v, how fast an object is going relative to them, and say, okay, based on what I measured for the dt between two events, and based on what I measured for the speed of an observer traveling between those two events, here's what their d tau value should be. And someone else can come along and say, well, I have a different dt value, and I have a different v value, but yep, with my dt and my v, I also get that number for d tau. So we're going to try putting something that everyone agrees on in the denominator and see what happens. So we get m dx over square root of 1 minus v squared dt, or mvx over square root of 1 minus v squared. And vx and v are both measured in the same frame. We're not getting one of them from one person's frame and another from another person's frame. If we see a rocket taking off and I'm sitting on the ground, I measure the velocity of that rocket using my equipment at rest with respect to the ground. And you were flying in an airplane that was going to observe that rocket launch, and you are going to get a different measurement of v, but you use your measurement. And then we get similar things for the y and z components of momentum. And then since it's relativity, and in relativity, we also keep transforming time. Somebody says, hey, let's define a time component of momentum. And you say, what on earth is that? And what we say is, that's called delayed gratification. We're going to have to wait a couple of slides until we get to an interpretation of it, but let's just try. Any questions so far? All right, seeing none. Well, it's a really easy thing to work with when we jump between reference frames. If I want to jump to a new reference frame, px prime is going to be m dx prime over d tau. We don't have to change tau when we go from one reference frame to another because, again, everyone agrees on what d tau is, or at least everybody says, hey, yeah, I'm watching the people on that spaceship. I think they measured this for d tau. Somebody else says, well, I'm also watching them, and I'm in a different reference frame. But yeah, I agree with you on what the people in that spaceship should measure for d tau. So if we transform to another reference frame, the thing in the denominator doesn't change. The thing in the numerator changes just like x would change. So we get dx d tau minus beta dt d tau, or gamma times px minus beta pt. Now we have to be very careful. This gamma has 1 over square root of 1 minus beta squared. It's the velocity it's the relative velocity of two reference frames. So if I'm on the ground, you're in an airplane, and we're both watching the rocket launch, this gamma here is going to have the speed. If I'm going from my reference frame to yours on the airplane, this is going to be the speed of the airplane. And in my dx d tau, I'm going to have a square root of 1 minus v squared in the denominator. And that v is going to be what I measure for the rocket velocity. Okay? So this is going to be, if I'm going from my reference frame on the ground to yours in an airplane watching the rocket, this is what I say, this is what I measure for your velocity in the airplane. This is what I measure for the rocket velocity. Then py prime, well, dy doesn't change when we go from one reference frame. So py prime is the same as py. Pz prime is the same as pz. And pt prime also transforms just like time does. So if px, py, pz, and pt are conserved in one frame, then they're conserved in all frames, because the change would be 0 in one frame. And then we go to another frame, we'd say, all right, delta px in the other frame is gamma times delta px minus beta delta pt. So we got gamma times 0 minus beta times 0. Let me think, nothing, add nothing, carry the nothing, that's nothing. So we've got something that is defined in such a way that if the change is 0 in one reference frame, it's 0 in all other inertial reference frames. Any questions? Now, to be careful here, what I've proved is that if these things are conserved in one frame, then they're conserved in any other inertial reference frame. I didn't prove that these things are conserved, all right? I have not proved to you that this version of px over here is conserved, whereas this version, the Newtonian version, isn't. All I've proved to you is that if we have a quantity defined this way, and if it is conserved in one reference frame, then it's conserved in any other reference frame. That's all I've proved to you, right? Proving that these things are conserved, well, that happens every day where people, it's not that people literally every day say, let's check conservation, but every day people collide particles together. They collide those particles to do fundamental physics experiments. They collide those particles to make isotopes for use in medical tests, isotopes for use in various industrial processes. They watch particles decay, sometimes for experiments to test ideas, sometimes to generate nuclear power, sometimes to do medical imaging. And every single calculation done for designing one of those instruments or one of those experiments is based on the idea that these quantities are conserved. And the experiments work. They make the isotopes that they need for the medical tests. They do the positron emission tomography. The Large Hadron Collider keeps running. And while it doesn't always find what they were hoping to find, all of the results that they get add up. It's not like they watch a particle decay in a way that violates all of the conservation laws. Sometimes they see a particle decay in a way that was unexpected, but it just means that other things are happening. It doesn't mean that what's happening doesn't conserve momentum and energy. Any questions? Very practical example. There's something called technetium. It's one of those isotopes that's in the middle of the periodic table, and it's one of the few intermediate mass not isotopes, elements. It's one of the few intermediate mass elements that isn't stable. You know how most elements have both stable and unstable forms? Like hydrogen has two stable forms, hydrogen and deuterium, and an unstable form, tritium. Carbon has a few stable forms, the most common being carbon-12 and carbon-13. But then there's carbon-14, the radioactive stuff that archaeologists use to figure out how old specimens are. Well, technetium is one of the few elements that doesn't have, one of the few elements in the middle of the periodic table that doesn't have any stable forms. But it gets used as a gamma ray source in diagnostic tests. And so in order to use it as a gamma ray source, they have to produce it. It's produced in linear accelerators every day for diagnostic tests. And accelerating particles to those very high energies, relativity factors into the calculations, and it works on a daily basis. I'm harping on this because there are crackpots who like to say that Einstein was wrong. Einstein might have been wrong, but if Einstein was wrong, the errors are going to be very subtle. And in all of the experiments that people do every day, those errors are only going to show up many, many decimal places away, so many decimal places over that they don't produce a detectable discrepancy. Anyone who claims that there's a glaring error in Einstein's work is just completely wrong. You can ask anyone who works at a nuclear power plant. All right, so let's interpret these quantities. Well, at low speed, this denominator is 1. So, or very, very close to 1, so we get mvx. Now PT, we have to do a little more with it. We've got m over square root of 1 minus v squared. That's m times 1 minus v squared to the negative 1/2. So we'll do a Taylor series. 1 plus u to the n is 1 plus nu for small u. And by the way, this is reviewed in, I think, chapter 3 of that book we're using in fall for math methods, the one that I recommended you study. Wouldn't hurt to buy it over the summer. That's reviewed in chapter 4. There might be, no, there isn't anything on that in chapter 2. Chapter 4. All right. So we get m times 1 plus negative 1/2. That's the n, the exponent, times minus v squared, or m plus 1/2 mv squared. And if we switch from grown-up units to the units that we use to compare with measurements, then we've got mc squared plus 1/2 mv squared. And this is the non-relativistic kinetic energy. And this is the energy needed to create a particle. This is Einstein's famous E equals mc squared. So PT is mc squared plus kinetic energy, or kinetic energy is energy minus m, or energy minus mc squared, depending on your units. Now at this point, somebody always asks, so wait, so m over square root of 1 minus v squared minus m is 1/2 mv squared? Not in general, only if v is very small. If I just tell you, hey, here's the energy that we use to create this particle, or here's the total energy of the particle. In relativity, energy includes mass. So in relativity, energy is mc squared plus kinetic energy. If I told you that an electron had an energy of 611 kilo electron volts, or 0.611 mega electron volts, well, mc squared is 0.511, so it would immediately follow that its kinetic energy is 0.1 mega electron volts, or 100 kilo electron volts. Any questions? I just tossed the most famous equation in physics at you, E equals mc squared. Somebody must have a question about E equals mc squared. Come on. Somebody must. Nobody has a question about E equals mc squared? All right, so I see an error in this table I compiled. First part's right. If somebody put an electron through a voltage difference delta V to change its kinetic energy, then, or to give it kinetic energy, starts at rest, accelerates through delta V, 0.511 MeV plus charge times the voltage difference, that would be equal to m over square root of 1 minus v squared. So in order to find the kinetic energy, we'd have to take this quantity, subtract off that quantity. Now, a convenient fact is that protons and neutrons have masses very close to a giga electron volt, very close to a billion electron volts. The muon is just like an electron, except it's 200 times the electron mass. And for some reason, I wrote mega electron volts when I meant to write 200 times the mass of the electron. I'll correct that after class. Any questions? You guys are killing me. No questions on E equals mc squared? All right, these four components of momentum form something that physicists call a four vector. Now we need to be very careful because mathematicians have a different definition of a vector. Up till now, in 3 dimensions, everything that you've learned about vectors in 3 dimensions in physics is completely consistent with vectors in linear algebra, whether we're talking about 3 dimensions, 4 dimensions, n dimensions, whatever. The 3-dimensional vectors that we use in physics are consistent with everything you learn about vector spaces in linear algebra. But then things get weird because 4-dimensional space-time has different properties than 3-dimensional Euclidean space. For starters, let's look at this quantity pt squared minus px squared minus py squared minus pz squared. Well, that's going to be m squared times delta t squared minus delta x squared minus delta y squared minus delta z squared. All right, well, that's something that we know about. That's delta s squared up top. And on the bottom, we have delta tau squared from the definition. And for very short intervals, delta tau and delta s are the same. So we get that pt squared minus this, the notation gets weird here, okay? If I write p vector magnitude, that means the length of the usual 3-dimensional momentum vector that you're used to, px, py, pz. So pt, so length of p squared, if I just write p vector, that is px squared plus py squared plus z squared, plus pz squared. So pt squared minus p squared equals m squared. But this quantity also gets called a length. We also refer to this as the length, or the length of a 4 vector. Now, that's fine for momentum, for this energy momentum 4 vector, because the squared length of this energy momentum 4 vector is m squared. It's a positive number. So if we have this energy momentum 4 vector, the thing that we call a squared length is a positive number, no problem. But of course, we know that sometimes, we learned last class, that there's no guarantee that this s squared is positive. If the separation between 2 events is space-like, then this s squared could be negative. So we have this very unfortunate terminology where we call something the squared length of a vector, even though sometimes it's a negative number, which means that it doesn't satisfy the definitions of a vector in mathematics, where people talk about vector spaces, but it becomes a 4 vector. Now, of course, in mathematics, people have 4-dimensional vector spaces. They're just one type of n-dimensional vector space. And so there's an unfortunate confusion of terminology here. I wish I could do something about it, but it's a bit like British versus American English, where there's a few words that just have different meanings. And unfortunately, the only ones that are coming to mind right now are the ones that lead to unfortunate confusions that I can't discuss at work. But that sort of illustrates the point that because of differences in terminology, sometimes things that make perfect sense in one setting would be at a minimal nonsense and at worst offensive in another setting. And likewise, in physics and math, what we call a four-vector does not mean a vector in a Euclidean four-dimensional space. It means something in space-time. Somebody's got to have a question. I'll just make this awkward and do nothing and check my text until someone asks a question. Text from my gaming group. Somebody's got to have a question about definitions of four vectors. E equals mc squared.
Professor, I have a question for in page 5 when you're defining PT, of mc squared plus ke. So for ke is like approximately 1/2 mv squared, but if v is like really low, and that equals, so that would equal to 1, and 1 minus 1 is 0. So pt, which is equals mc squared. And
No. This, unless v is 0, this is not 0. It may be small. It may be that the kinetic energy is much less than mc squared. Most of the kinetic energies that we deal with on a daily basis are very tiny compared to mc squared. That doesn't mean they're 0. All right? I mean, I just bought a power tool yesterday. The kinetic energy of everything in that power tool is way less than mc squared. But believe me, if I used it incorrectly, I would notice that kinetic energy. So kinetic energy is not, in general, 0. It's just way less than mc squared. Does that help?
Yeah. Because I often hear the equation of like E equals mc squared for only like resting objects or something like that. Okay.
If an object is at rest in your reference frame, then E equals mc squared. If it's not at rest, E is not mc squared. It's something else. You may be thinking, then why did people like on TV and in popular books just say E equals mc squared? And the answer is quite simple. They don't know what they're talking about. All right, so PT is mass plus kinetic energy. It's the energy to make an object and accelerate it. And so E has this, again, we see another parabolic plot. E versus P looks like this. And there is this negative branch, and that actually shows up in relativistic quantum mechanics. It's related to antimatter, but we're not going to say much about that for now. Let me give an important example, the neutrino. The neutrino is a particle created in nuclear decays, and it has a tiny mass. In fact, its mass is so tiny that nobody has ever accurately measured it, but we do know that it's non-zero for very complicated reasons. Because this mass is so tiny, almost all of the time we get the reverse of our typical daily situation. In our typical daily situation, kinetic energy is way less than mc squared, which is just another way of saying that P is much less than M. But here we get the opposite, all right? If we've got the E squared minus P squared equals M squared, then we could say that E squared is P squared plus M squared. Or if you are not working in grown-up units, P squared C squared plus M squared C to the 4th. So you could go over here, and now in most experiments, P will be the large number, M will be the small number, so we would factor it like this, all right? We pull out P, the large number, and we're left with square root of 1 plus M squared over P squared. and we would get that the energy is roughly P plus m squared over 2p, which is completely the opposite of what we normally get, where we say that E is mc squared plus 1/2 mv squared or p squared over 2m. You may be thinking, why p squared over 2m instead of 1/2 mv squared? But remember, the p is mv, so what we've really got here is m squared v squared over m, or mv squared. Any questions? All right, so let's do an example. Let's accelerate a 1 kilogram mass to 3/5 the speed of light. Well, we plug in some numbers and we get 2.25 times 10 to the 16 joules for the kinetic energy, because the energy itself is this. But then we have to subtract off mc squared to get the kinetic energy. Because remember, if I want to accelerate something, well, if the object already exists, then I don't need to spend mc squared to create it. That's already been done. I just need to spend m over square root of 1 minus v squared minus mc squared, the kinetic energy. So to accelerate 1 kilogram to 3/5 the speed of light, we would have to spend this much energy, which would be about 500 large nuclear bombs. Since a large nuclear bomb, last time I Googled it, is roughly 5 times 10 to the 14th joules. So as much as I love sci-fi scenarios of people traveling close to the speed of light, it's important to emphasize the phi in sci-fi, the fiction in science fiction. It is very unlikely that we're ever going to accelerate very large spaceships or even very small spaceships. I can assure you that a small space capsule has a mass of way more than 1 kilogram. You'd need 500 nuclear bombs just to produce the kinetic energy to get 1 kilogram going at 3/5 the speed of light. Or let's break this down from the scale of nuclear bombs to the scale of subatomic particles. The fission of a uranium-235 nucleus, and by the way, this is the notation for an isotope. You've got the atomic symbol, you've got the mass of the nucleus, so the number of protons and neutrons, and then you've got the atomic number, just the number of protons. You might say that the atomic number is redundant with the chemical symbol. And personally, me, myself, and I all agree with you that that's redundant, but nonetheless, that's how we communicate. All right, so that fission gives 200 mega electron volts. All right, that's 400 electron masses. On the other hand, that's only 1/5 of a neutron mass. And let's suppose that all of that energy went into accelerating a neutron. And many times in nuclear decays, I wouldn't say all of it, but a substantial proportion of it does go into accelerating a neutron. So what would the velocity of that neutron be? Well, let's see here. The energy would be mass plus kinetic energy, mn plus 0.2 mn. And then we set that equal to the neutron mass over square root of 1 minus v squared. So we can cancel the neutron mass. We get 1 over square root of 1 minus v squared is 1.2. We do the algebra. We get that v squared is 0.3. And we get that v is about 0.55. So a neutron in a nuclear reaction could very easily be going at a substantial fraction of the speed of light. And these effects do have to be taken into account when doing the calculations for a nuclear reactor. And they work. Nuclear reactors exist and they work. And many countries, actually not that many, but France gets a whole lot of its energy from nuclear power. And so that's a very good thing as far as carbon output. The only thing I'm going to say about politics is that while Andrew Yang has his strengths and weaknesses, I wish people had paid more attention to what he said about thorium reactors. Because if you want low carbon energy, nuclear power is where it's at. Whether that power is fission or fusion, fission has, do you know what the one big advantage is for nuclear fission over nuclear fusion? Fission reactors exist. That's an advantage worth taking into account. Any questions on those calculations? Anyone? All right then. If you have no questions for me, I've got questions for you. So we're going to vote here. I need to pull up the question. True or false? The x component of momentum is always equal to or smaller than, the Newtonian x component of momentum is always equal to or smaller than the x component of the 4 momentum, or essentially the x component of the relativistic momentum. True or false? So thank you. Heaven from hell. How I wish you were here. All right. 4 more people need to vote. Three more people need to vote. 2 more people need to vote. Students 7 and 8. Spasibo, student 7. Come on, student number 8. Vosam, that's Russian for 8. A bunch of fignia. You're not going to vote? Fine. Okay, so 5 of you said that this statement is true. And while democracy may not have led to a proliferation of nuclear power, it did lead to the correct answer on this one, because for some reason the textbook likes to use the slash through px when talking about Newtonian momentum. But the relativistic momentum is Newtonian momentum divided by something less than or equal to 1, which means you're multiplying by something greater than or equal to 1. All right, likewise, mass is always equal to or smaller than the time component for momentum. So let me pull up the next question for you to vote on. PT is always, another way to think about this is the PT is always greater than or equal to M. All right, we have 3 people voting. Chateri, Piat. Come on, where's Shest? That's Russian for 6. Where's student number Shest? Shest, do we have Sam? Do we have Sam? Do we have 7? Very good, we have Sam. Do we have Vosam? 8. Vosam? Come on, student Vosam. Come on, student number 8. Give it a try. Democracy's been working so far, so give it a try. All right, again, democracy worked because the time component of momentum is m over square root of 1 minus v squared. So it's m over something less than or equal to 1, which means m times something greater than or equal to 1. So yeah, the time component is always greater than or equal to the mass. So the mass is always less than or equal to the time component. All right. Now, the absolute value of the x component of the momentum vector is always equal to or smaller than the t component. And they say absolute value because, you know, px could be positive, it could be negative, depending on direction. Right now, we're just caring about the magnitude. Is that magnitude equal to or less than the time component? True or false? So I will launch that question. Dva people voting. Tree. Chiteri. Piat. Shest. Do we get Sem? Don't worry, I can't see who's voting. So if you're worried that I'm going to see that you got it wrong, I have no idea who cast what vote. Sem, do we have vote, Sem? Yet? I'm just up here having fun, Tovarishi. Come on. Can I get Vosem? Student number 8. All right, well, they explain it one way. They say that PT squared minus PX squared minus PY squared minus PZ squared, that's equal to M squared. So PT has to be bigger than all of these. That's one way to see it. The other way to see it is that PT and PX both have M over square root of 1 minus V squared, excuse me. M over square root of 1 minus V squared. They've both got that. But PX also has that factor of VX. And the absolute value of Vx is always less than or equal to 1. So it follows that Px has got to be less than Pt. Any questions? Okay. Another question. We're going to first do part A. Parts A and B, we're going to do these together. So part A says that the squared magnitude of a 4 vector could be negative, true or false. Part B says that the squared magnitude of a 4 momentum could be negative, true or false. So you've got 4 options, both true, both false, one or the other. Tree. Chiteri. Four votes so far. Piat. Shest. Sam. Do we have votes, Sam? I think student Vosam is off in their own little Soyuz capsule. All right, so let's break this down. A is true. The way we have defined squared magnitude, even though it should make all good math majors cry, we've defined it as the time component squared minus the x component squared minus the y component squared minus the z component squared. So that could certainly be negative. In fact, when we talked about events with space-like separations on Monday, we got cases where the squared magnitude or the space-time interval squared was negative. But 4 momentum is not just any old 4 vector. 4 momentum is a very specific 4 vector. And that very specific 4 vector, its squared length is always equal to mass squared. So that very specific 4 vector cannot have a negative squared magnitude. Any questions? Let's do at least one more. All right. How does relativistic kinetic energy compare with Newtonian kinetic energy when the speed is 4/5? Is the relativistic kinetic energy less than 1/2 mv squared, greater than 1/2 mv squared, or exactly equal to 1/2 mv squared? Six votes, one more vote. All right. Yep, it's greater. The way to think about this is that we know that at small velocities, they're nearly equal. They're not quite equal, but they're nearly equal. At large velocities, as v approaches 1, the total energy diverges because the total energy is m over square root of 1 minus v squared. So the total energy is going to infinity. So total energy minus mass is also going to infinity, which means kinetic energy goes to infinity. Whereas the Newtonian kinetic energy just goes to 1/2 m when v equals 1. Any questions on that? Well, at this point, it is 10:51. On Friday, I'm going to say a little more about Chapter 8. We're going to do a few more of these questions, and then we're going to spend Friday and Monday on Chapter 9. I spent 2 days on Chapter 9 because those problems are, on the one hand, I think the most practical applications of relativity, and on the other hand, they take the most reworking. Well, they don't take the most reworking of intuition. I think the time takes the most reworking of intuition. But they're the most practical things, and they definitely require getting over some Newtonian habits. So we'll pick up there on Friday. Have a good day.